In this video, I will show you how to use the simplex method to solve a linear programming problem. You will see an example first. At the end of the video, I will summarize the steps of the method. The key concepts such as entering variable, leaving variable, ratio test, and pivoting will be introduced. This is a linear programming problem. It's a maximization problem with two variables. We need to convert it into the standard form by introducing two select variables, S1 and S2, to make these equality constraints. All the variables are greater than or equal to 0. After we get the standard linear programming problem form, we rewrite the objective function and move the right-hand side to the left and make it equal to 0. The objective function is changed to this, and it is marked as row 0. The two constraints are marked as row 1 and row 2. This is called the simplex canonical form. It is a system of linear equations in which each equation has a variable with a coefficient of 1 in that equation and a 0 coefficient in all other equations. We can put this canonical form in a table. These are the variables z, x1, x2, s1, s2, and the right-hand side. We write the values of the parameters in the corresponding cells in the table. For example, the coefficients of the variables in row 0 are 1 for z, minus 3 for x1, minus 2 for x2, 0 for s1, 0 for s2, and the right-hand side is 0. We do that for row 1 and row 2 as well. Finally, this is called the simplex tableau. If we do not count z, we have n is equal to 4 variables, x1, x2, and s1, s2. We have m is equal to 2 constraints. Therefore, we can set n minus m is equal to 2 non-basic variables to 0, and so for the remaining m is equal to 2 basic variables. We can pick the variables that appear with a coefficient of 1 in a single equation and not in all other equations as basic variables. For example, S1 has a coefficient of 1 in row 1 and is not in other rows. It's a basic variable. So is S2. The other two variables, x1 and x2, are non-basic variables. Let's set x1 and x2 to 0 and solve for s1 and s2. This part will be gone. We have s1 is equal to 9, s2 is equal to 9. In row 0, we have z is equal to 0. As a general rule, a select variable can be used as a basic variable if the right-hand side of the constraint is non-negative. If the right-hand side is negative, then you cannot use a select variable as a basic variable because it will violate these sign restrictions. Let's write out this basic feasible solution. S1 is equal to 9, S2 is equal to 9, x1 is equal to x2 is equal to 0, and z is equal to 0 for this basic feasible solution. Here is a question. Can the objective function z, which is equal to 3 times x1 plus 2 times x2, be improved by increasing some non-basic variable from its current value of 0 while holding all other non-basic variables at 0? Right now, the two non-basic variables are x1 and x2. They're both 0. If we increase x1 from 0 to 1, the z value will increase from 0 to 3. If we increase x2 from 0 to 1, the z value will increase from 0 to 2. So increasing either non-basic variable will increase z. The current basic feasible solution is not optimal yet. Increasing x1 will cause a greater rate of increase of z. Let's check the tableau. x1 has the most negative coefficient in row 0. If we increase x1 from 0 to a positive number, it will become a basic variable. Because it is entering the set of basic variables, we call x1 the entering variable. Now we need to determine the largest we can make x1 so that all basic variables are still non-negative. For that purpose, we need to compute a ratio for every constraint in which the entering variable has a positive coefficient. This ratio is the right-hand side of each constraint row over the coefficient of the entering variable x1 in that constraint row. The constraint with the smallest ratio is called the winner of the ratio test. Let me show you what it actually means. For row 1, if x1 is no longer 0, we have to write out this item, 2 times x1. x2 is still a non-basic variable, so its value is 0. s1 is a basic variable, so we put it here. We don't have s2 in the equation because the coefficient is 0. The right-hand side is 9. We rewrite this equation by moving 2x1 to the right-hand side. We have s1 is equal to 9 minus 2 times x1. Due to the sign restriction, s1 is greater than or equal to 0, so x1 is less than or equal to 4.5, which is the right-hand side in this row divided by the coefficient of x1. For row 2, if x1 is no longer 0, we have to write out this item, 1 times x1. x2 is still a non-basic variable, so its value is 0. s1 has a coefficient of 0, so we don't have it in this equation. s2 is a basic variable, so we put it here. The right-hand side is 9. We rewrite this equation by moving x1 to the right-hand side. We have s2 is equal to 9 minus x1. Due to the sign restriction, s2 is greater than or equal to 0. So x1 is less than or equal to 9, which is the right-hand side in this row divided by the coefficient of x1. Now we have two upper bounds, 4.5 and 9. To satisfy all the sign restrictions, we have to select a smaller value, which means the largest value we can increase x1 to is 4.5. This is the actual meaning of the ratio test. So row 1 wins the ratio test. We need to make x1 a basic variable in this row. It means that we should use elementary row operations or EROs to make x1 have a coefficient of 1 in row 1 and a coefficient of 0 in all other rows. This procedure is called pivoting on row 1, and row 1 is called the pivot row. x1 will replace s1 as a basic variable for row 1. S1 is called the leaving variable because it leaves the set of basic variables and becomes a non-basic variable. I'll show you how to do the EROs step by step. We change this coefficient to 1 by dividing 2 for both sides. This new row is called row 1 prime. 2 divided by 2 we get 1. 1 divided by 2 we get 1 over 2. 1 divided by 2 we get 1 over 2. 9 divided by 2 we get 9 over 2. Then we remove this coefficient in row 0 by adding 3 times row 1 to row 0. It's called row 0 prime. This will be gone. This will be changed to minus 1 over 2. This 3 over 2. And the right-hand side is now 27 over 2. Now we remove this coefficient in row 2 by subtracting row 1 prime from row 2. It is called row 2 prime. This will be gone. This will be changed to 3 over 2. This minus 1 over 2. This is 1, and the right-hand side is now 9 over 2. In this tableau, the coefficient of x1 in row 1 prime is 1, and the coefficients in all other rows are 0. So we are done with the EROs and pivoting. This is a new tableau. Now the basic variables are x1 and s2. And non-basic variables are x2 and s1. We set non-basic variables to 0 and solve for the basic variables. The basic variables are x1 is equal to s2 is equal to 9 over 2. The z value is 27 over 2. What actually happened was that we used the pivoting procedure to go from one basic feasible solution to a better adjacent basic feasible solution with the largest z value. This is called an iteration. Let's write out this basic feasible solution. x1 is equal to 9 over 2. s2 is equal to 9 over 2. s1 is equal to x2 is equal to 0. z is equal to 27 over 2 for this basic feasible solution. Here is the question again. Can the objective function z, which is equal to 27 over 2 plus x2 over 2 minus 3s1 over 2, be improved by increasing some non-basic variables from its current value of 0 while holding all other non-basic variables at 0? Yes, if we increase x2, the z value will increase, so the current basic feasible solution is not optimal yet. Let's check the tableau. x2 has the most negative coefficient in row 0 prime, so x2 is the entering variable. Now we need to do the ratio test to find out which row will be the pivot row. We find out that row 2 has the smallest ratio, so it will be the pivot row. We need to make x2 a basic variable in this row. It means we should use EROs to make x2 have a coefficient of 1 in row 2 prime and a coefficient of 0 in all other rows. This time you can try it yourself. I'll just quickly show the results. We replace row 2 prime by 2/3 of row 2 prime. Now add a half of row 2 double prime to row 0 prime. Subtract a half of row 2 double prime from row 1 prime. Finally, this is the updated tableau. Now the basic variables are x1 and x2, and non-basic variables are s1 and s2. We set non-basic variables to 0 and solve for basic variables. The basic variables are x1 is equal to x2 is equal to 3. The z value is 15. So we used the pivoting procedure to go from one basic feasible solution to a better adjacent basic feasible solution with the largest z value. This is the second iteration. Let's write out the basic feasible solution. x1 is equal to 3, x2 is equal to 3, s1 is equal to s2 is equal to 0, and z is equal to 15 for this basic feasible solution. Increasing s1 or s2 will not improve z, so the current basic feasible solution is optimal. As a general rule, a canonical simplex tableau is optimal for a maximization problem if each non-basic variable has a non-negative coefficient in row 0. To sum up, we can use the following steps to solve a maximization linear programming problem. Step 0. Convert a linear programming problem into a canonical simplex tableau. Step 1. Obtain an initial basic feasible solution from the simplex tableau. Step 2. Determine if the current basic feasible solution is optimal by checking if all non-basic variables have non-negative coefficient in row 0. Step 3. If not, determine the entering variable and which row to pivot on. The entering variable has the most negative coefficient in row 0. The pivot row is the row that wins the ratio test. Step 4. Use EROs to find a new basic feasible solution with a better objective value. Then go back to step 3. For a minimization problem, we can convert it to a maximization problem by maximizing the opposite of the objective function. Okay, that is the simplex method for solving linear programming problems. Thanks for watching.